Hi, I'm Prashant and she's Tirumala. In this video, we are going to explain about shell momentum balance on falling film. From here, she will give the introduction of our topic.
In this video, we specially focusing on the flow of falling fluid. Imagine the thin layer of liquid is flowing down inclined to the solid surface. Like water is sprinkled down the window and oil coating a wall. This phenomena is not just for just common in a nature, but also it is crucial in industrial process like uh, coating distillations and chemical reactors. Today we will break down the physics step by step from Newton's law of viscosity to calculating velocity profile and the partial applications. First, let's revisit the Newton's law of viscosity, the foundation of our discussion. It describes how viscous force act in a fluid. It states that the shear stress is flowing fluid is directly proportional to the rate of shear strain. In mathematical, tau is directly proportional to the change in velocity upon change in direction. We replace the proportional we replace the coefficient of proportionality with viscosity. Viscosity is also called as the uh, dynamic viscosity. Significance of the Newton's law of viscosity. The fluid which follows Newton's law of viscosity are called Newtonian fluid. So far we talked about simple 1D flow, like honey is sliding straight down a flat plate. But in real life, fluids move in all directions. Think about a river swirling around the rocks and or oil churning in a mixer. To describe this complex motion, we need a 3D version of Newton's law of viscosity. In 1D, set stress was single number like 0.5 newtons per meter square, but in 3D stress becomes a tensor. Okay. Now imagine we are going to talk about the fundamental shell momentum balance. The shell momentum balance approach, the how it can be used to solve a very simple problem. So we have identified that in shell of a fluid, some fluid is coming in and some fluid is going out, and there can be also variation in velocity which exists in fluid. So when something is flowing in a control value, it comes in with horizontal. Now we are going to talk about the fundamental of shell momentum balance. The shell momentum balance approach and how it can be used to solve a very simple problem. So we have identified that in a shell of a fluid, some fluid is coming in and some fluid is going out, and there can be also variation in velocity which exists in a fluid. So when something is flowing in a control value, it comes in with a velocity. Some mass of fluid coming in with the Now we will discuss about the generalized shell momentum balance equation. Rate of momentum in by convective transport minus rate of momentum out by convective transport plus rate of momentum in by molecular transport minus rate of momentum out by molecular transport plus forces of gravity acting on a system is equal to 0. Generalized methods of shell momentum balance. Select the coordinate system and origin. Identify the non-vanishing velocity component and the variable on which it depends. Write the momentum balance. Let the thickness of the shell approach 0 and make use of definition of the first derivative to obtain the corresponding differential equation for the momentum flux. Integrate this equation to get the momentum flux distribution. Insert Newton's law of viscosity and obtain the differential equation for the velocity. Integrate this equation and use appropriate boundary condition to get the velocity profile. Velocity distribution. Use the velocity distribution to get the other quantities such as maximum velocity, average velocity or force on solid surfaces. Now we discuss about the boundary condition which are used in this scenario. Solid fluid interface plane, no slip condition. Liquid interfacial plane, modified no slip condition. Liquid gas interface plane, zero flux condition. From here Prashant will be continue the explanation of the remaining problem.
Our problem statement is as follows. Consider the flow of a liquid down an inclined flat plate of length L and width W as shown in figure. The inclination angle of flat plate is beta and the thickness of film over plate is kept constant delta with the reservoir at the top. If delta is very small as compared to length and width, derive the equation for velocity and momentum flux profile and hence develop the equation for maximum velocity, average velocity, mass flow rate and drag force on blade. Viscosity and density of the liquid is assumed to be constant. Neglect all effects because of disturbances. The gravity is acting in this direction with an angle in this direction, downwards direction of, this is direction of gravity, and this is the liquid flow in, and this is our reservoir. And the thickness of film is delta. This is liquid film. This is the angle of inclination of the plate, and this is the length of the plate is L. Here we have some entrance disturbances, and here we have some exit disturbances. So let's assume some assumptions to make this problem simpler. The first assumption is the flow is steady state. By steady state we mean that velocity is equal every point of the flow, and the second assumption is the flow is laminar. And third assumption is viscosity and density of liquid is constant, and effects are neglected. Here in the diagram we can velocity is only in this direction. Velocity does not exist in the horizontal direction and the vertical direction. It exists only in the direction of inclination because of the gravity force. So we can say that this is a 1D flow. Let's show our flow in 3D form. Here we consider quotation or our coordinate system as quotation system, and we can take origin anywhere at any corner of this flow, but we consider our origin at this point. This is our x direction, and this is our y direction, and this is our z direction. And this is the length of the plate, that is L, and this is the thickness of our film, that is delta, and this is a width W. The flow is in this direction, z direction. So from here we can say that here at this point the velocity is 0, and at this point at this layer of the flow film, velocity is maximum. This is called the no slip condition. At this point momentum transfer is maximum, and at this point momentum transfer is minimum. This is called as no shear condition, because the momentum transfer is 0 at this layer of the film. Now let's talk about the velocity. Velocity exists only in z direction because flow is in this direction, and velocity is 0 in y direction and x direction because flow doesn't exist in x and y direction. So we can say that Vx and Vy are 0 and Vz is non-zero, and we also say we can also say that Vz is a function of x, because at this bottom layer of the film the velocity is 0, and as we increase the we go from bottom to top, velocity increases gradually. So velocity is a function of x. And pressure is also function of x. From the formula we know that from the formula rho g h, as height increases, well, pressure also increases. So from top to bottom pressure changes. Pressure is minimum at this point and maximum at this point. So pressure is a function of x. Now let's select our differential element. This is our diagram of our complete flow, and from this diagram we select our differential element for the study purpose, to make the to simplify the study. So our differential element is dimensions of element. In x direction, our differential element is here x is equal to x2, x is equal to x plus delta x, And in z direction or differential, we consider a differential element from z is equal to 0 to z is equal to L, and the length of the this plate is L. And in y direction, width is taken from y is equal to 0 to y is equal to W. This is our width, and this is the thickness of the differential element, and this is the length of the differential element. Dimensions of our differential element: in x direction, x is equal to x2, x is equal to x plus delta x. In z direction, z is equal to 0 to z is equal to L. And in y direction, y is equal to 0 to y is equal to W. This is the thickness of the element, and this is the length of the element, and this is width of the element. Till now we have discussed about the problem statement, assumptions, boundary conditions, and the differential element. Now let's derive the flux profile and velocity profile. We start our derivation with total flux formula. Total, we know that total flux is equal to molecular flux plus convective flux, and we know molecular flux is equal to pressure into del Ij plus tau Ij, and convective flux is equal to rho Vi and Vj. Now total flux is denoted as pi Ij is equal to P del Ij plus rho Vi Vj plus tau Ij. And tau Ij is the generalized Newton's law of viscosity. It is written as generalized Newton's law of viscosity. It is written as tau Ij is equal to minus mu into dou Vj upon dou Xi plus dou Vi upon dou Xj plus 2 by 3 mu minus k into del Vx by dou Vx by dou X plus dou Vy by dou Y plus dou Vz by dou Z into del Ij. Here we know del Ij is equal to 0 and del Ii is equal to del Jj is not equal to 0. Here tau Iz is we can call this a momentum in I direction due to velocity in z direction. If we take it as tau xy, then we can say this as momentum in x direction due to velocity in y direction. If the velocity is in x direction, then its momentum will be in all the three directions, in x direction, y direction, and z direction. So we can write this as tau xx. It means velocity in x direction and momentum in x direction, and tau xy yx. It means velocity in x direction and momentum in y direction, and tau zx. It means velocity in x direction and momentum in z direction. We can also say this as momentum in z direction due to the velocity in x direction. In the same way, if the velocity is in x direction, we have three components of momentum. In the same way, if the velocity is in y direction, then we have three components of momentum, and if the velocity is in z direction, we have three components of momentum. Then we will get nine components of momentum due to velocity in three directions.